primarily being a storage. So NetApp being a storage company in the last 3 decades, you can find out there are like tens of thousands of customers who use NetApp storage for their unstructured and structured data. And as of now, there are like 80% of the data is unstructured, and most of the data is not utilized as the way it was before generative AI. So what generative AI actually brought to the table is like you can use the large language models, which is pre-trained, at a click of an API call, and then you can actually give the data to them, to the large language model, which actually creates a synthetic data generated from the large language model. How do we do that? It's a big process on the pipeline, but it actually brings it easier right now, because the way it works, like 2 years back, the enterprise customers have to build their own model, deploy their own model, and they have to build the whole pipeline. But right now the major cloud providers and also NVIDIA is bringing to the table by basically providing you an API call. So that's what we're going to talk about it today. And I want to thank my colleague Mike Oglesby, who worked with me on this solution. So we actually built this particular proof of concept within a 6 days time before NVIDIA GTC for getting it announced. Right. So as you can see here, this slide represents how NVIDIA and NetApp jointly works with NetApp customers and NVIDIA customers to help them connect their external data sources and use them as part of the RAG framework and the RAG UI to help them in the use cases with respect to helping the customer AI support, or also in the internal document accessibility. So those are the 2 major use cases what I see. And the internal document accessibility, NetApp also has a similar architecture, but not with NVIDIA, but with Microsoft. So most of the companies are doing that right now. So it's a simple example. If you're part of the law firm, and if you want to access large amount of data to get an inference out of it, so a lot of companies have started doing that using a pre-trained model, which is specifically based on the fin data or the data which is required by the law, and then use it with their own data set to get a better inferencing. So as you can see here, on the left-hand side, you can see it can be a document, or it can be a spreadsheet presentations. So it all depends on like what kind of model you are using. But very primitively, like it could be a PDF doc, or it could be a text or a JSON. It can be an unstructured file. It is a part of the data set, and it can be located anywhere. For example, in this case, the proof of concept what we did is basically on-premises and on the cloud. So when we talk about on-premises, we use the NVIDIA DGX cloud with NetApp ONTAP, and also on the cloud we used Google Cloud NetApp Volumes and Google provided GPU instances. So here the data is residing on ONTAP or the NetApp Volumes, which is on different cloud. So when I mean on-premises, it means the NetApp provided hardware, the storage hardware. When I mean cloud, the similar kind of services is provided by NetApp in the cloud across all the 3 hyperscalers. And what does the Nemo Retriever brings to the table, which is provided by NVIDIA? So this is basically Nemo Retriever. We got a private access. So any of the enterprises can go and get the private access for this Nemo Retriever. It's basically a RAG framework. It consists of multiple generative microservices together, and it helps the customers to enable the inferencing of their own private data set. So, and this is not generally available right now, but we had an opportunity to work with them to create a proof of concept and prove them it works with NetApp. So, and we are building solutions on top of this right now. On the right-hand side, you can see it could be a chatbot, it could be a copilot, it could be in any of the applications, AI-powered applications. Right now, you can see anywhere, like all the solutions or applications is basically AI-powered applications, which is backed by large language model. But the data sets is more critical. So the data sets are located on the NetApp right now for the customers who are having the NetApp storage, and then they can actually have any of the chatbot or any of the copilot or any of the applications connected to the enterprise data sitting on NetApp, by using NVIDIA NeMo Retriever. So NeMo Retriever provides the framework, which is basically a RAG framework. It helps chunks, embeds, and sends it across to the vector database of the choice, what it provides, and customers can use them to choose based on like what is requirement, and then they can actually use this index as part of the chatbot or the copilot or the application. Once again, let me minimize this. Yes. And what extra NetApp provides there is like the data management with respect to access control, the compliance of data, the disaster recovery, data security, and the cost optimization. The most important use case when it comes to RAG, the private data, is like data security. So none of the enterprise customers wants their data to be accessed outside. So in this case, by building the NeMo Retriever within your network, so you're making sure your data is not going outside. So that is more critical right now with all the enterprise customers. They want to have the private data within their data center. So that's what we actually have this way of saying like NetApp customers can talk to their data, meaning like it could be unstructured file right now, but in the future we will be always looking at supporting the structured files as well. Right, so this is a simple architecture to show like what we did with the proof of concept. So as you can see on the bottom layer, we have the data center or all the three clouds. So on the data center, we use the DGX cloud, which is backed by NetApp storage, and then we were running a Kubernetes as a compute. It can be any Kubernetes meaning it could be on the cloud or on premises. We did 2 prototypes as an example here with the DGX cloud, which is on premises, and which is and the other one is GCNV, because GCP, which is Google Cloud Platform, provides the GPU instances right now. So we did the prototype with that, and on the top layer you can see they basically call this as a NVIDIA NeMo family or NVIDIA Generative AI, where they have multiple services as a part of the NeMo family. And they're coming up with all these microservices. So one of the microservices what we utilize is Inference AI, which actually provides the inference which actually provides the API for the inference clients to get the data. And then the same NIM, which is like NVIDIA NeMo Inference Microservices, which has the search, which has the inference API and also the engine. And also we have this retriever. Retriever is like which actually connects between the data source and also the inference engine. So that's where the data is residing on the NetApp. The customer's data is sitting on NetApp storage. And also here the Kubernetes is backed by NetApp NAS storage, which means like the model which we deployed also is located on the NetApp storage. So everything is on NetApp storage here. The data is on NetApp storage. The model we deployed is on NetApp storage as well. So in this example, the NVIDIA has support for the community models and also for the NVIDIA models. So we use the Meta Llama, and what are the advantages it provides is NVIDIA provides for us is like you can customize a model for yourself. So right now, most of the models here supported on the GPU platform. So when we did our proof of concept, we were not getting the instances what we want from the Google Cloud Platform. It's very hard to get right now when we did the proof of concept. So we have to customize the model and then install the model based on the GPU instances what we got. So those kind of options are available with this NVIDIA platform. And they also give an option for customers. So in this case, we use PG Vector as the index, but they also provide Milvus and other options for customers. So it is configurable. It is a configurable part. So it is easy for customers to choose what they want, based on their requirement. Right. So this slide, it explains what are the existing data sources, what is supported from NetApp. So the ONTAP, it's basically on data center, and storage grid is also on the data center on premises. And the other 3 are Amazon FSx for NetApp ONTAP. That's the NetApp volumes on Amazon, which is sold and supported by Amazon, which is a first-party service. And then Azure NetApp Files, which is on the Microsoft Azure. on Google Cloud NetApp volumes. So all these are the data sources which could actually use with the Nemo retriever to ingest the data from the NetApp volumes into NVIDIA. So all the NVIDIA services what we ran is basically a microservices. As you can see, this is a simple architecture of the Nemo retriever. On the top left, you can see all those different data types, which is actually ingested into the embedding microservices. And you can see multiple microservices. For example, embedding microservices, retriever has a separating microservices, and re-ranking has a separate microservices. And also you have a PG vector, that is a different microservice. And if you choose a Milvus, that also has a different microservice. So on data, to process the data, that has a different microservice. Everything is running on a Kubernetes. So this is all configurable, and this is right now. This is how we can actually implement the NVIDIA Nemo retriever. And on the right-hand side, it showcases benefits like, so it provides a world-class accuracy. These are all the benefits what you get out of NVIDIA Nemo retriever. The one which I like is like the customizable models and pipelines. So right now, I think around like 1 year back, when I speak about the models, the 7 billion parameters was a large language model. So right now it is not. Right now, they mentioned the 7 billion is a small model. And then if it's a large language model, it's about 1.7 trillion parameters. So the models are getting updated as part of a rapid development. So the infrastructure also needs to keep up with that. This is a quick recap. I will share this particular slide. Please take a look at it when you have time. So these are the announcements what NetApp and NVIDIA made. So the key point here is like the NVIDIA announced NetApp has their storage partner program for the OVX platform, and also one of the feather in the cap for NetApp is like Jensen. As part of his keynote, he mentioned NetApp. So I was there. It was pretty awesome to experience that when NetApp was actually showcased in the keynote where Jensen was talking. Right. So this is about NVIDIA. I'm going to switch the context about like what we recently announced at Google Next. So we have a recent announcement from NetApp, which is Generative AI Toolkit for Google Cloud NetApp Volumes, which is announced very recently at Google Next. And we will be actually supporting for Azure as well. It's coming. So that got announced as part of the NetApp Converge. Right. So I'm going to talk about the GenAI toolkit today. So I'm going to a little bit explain the Google Cloud NetApp Volumes. That's because this is the first cloud NetApp Volumes which supported Generative AI toolkit. And personally, I like the Vertex AI platform, which provides good models, which could be integrated easily within the Generative AI toolkit. And these are the advantages what it brings to the table. So first of all, it's not a NetApp service. It's a Google service supported by Google. NetApp is backing the particular service in the Google Cloud. And then it supports multi-protocol. So you take any of the ONTAP data center features, it is supported. It's the same thing but running on the cloud, and it has all the major features which is provided by ONTAP in the cloud. So one of the features is the multi-protocol for enterprise workloads. And then as a user, they have the Google user experience, not NetApp user experience. You can go to the Google console. You can use it via Google API. There's a Terraform provider for Google Cloud NetApp Volumes, and it's also tightly integrated with the services like Google API, AID, cloud logging, major mandatory services within Google. And then it also brings the data protection and scalability. So you can actually spin up like 100 GB volumes into 100 terabytes within seconds. So that's rapid scaling, which helps in a lot of use cases. And then you can also do the synchronized data replication between regions. So that's available. And then you also have the snapshots volumes. These are the features what NetApp brings to the table. Right. And then let's take a minute talking about this. So what are the most demanding workloads right now with our partners and with customers, or like Windows-based applications, then SAP environment where we host and protect the SAP shared files. then extend your VMware with Google Cloud VMware Engine, then also supporting the mission critical applications on NFS, and then virtual desktops as service. These are the major workloads. Yeah. So interesting for me is like how we integrate with the Vertex AI platform. So we had like a year back, when we came up with this idea, like how can we enable NetApp customers to use the generative AI? So prior to that, it was more of a training. So we want to actually help our customers to train a model with the data set and then create an endpoint and then try to infer from that. But after generative AI, it was easy for us to actually help the customers to use the pre-trained model because it's by using the API endpoints. So in this case, what happens is that one of these top use case for the enterprise is like data security and data governance, where your data is not going out of the network, because we can have those applications running on the same VPC, or you can actually peer the VPC. It's basically within your network. It's not getting out of your network. That's more important for our enterprise customers. And as you can see here, the 3 points what we focused on is enterprise data is retained only on the NetApp volumes. And in this case, we also developed the DB, the vector DB, which will be residing on NetApp volumes. That is also one of the advantages, because we are not using any of the SaaS-based vector DB. In this case, we used Chroma. So Chroma is basically sitting on the NetApp cloud volumes. And then you have an administrator access control for the entire data set, and your enterprise data is not changed. So when I mean like enterprise data is not changed, so when you use a Vertex AI model, which is a large language model in any of the cloud providers, they provide a private instance for you, and they also guarantee that your data is not trained for their purpose. So which means you use a grounded model, and when you use the large language model provided by them with your data set, it uses only the pre-trained models, but it doesn't train the pre-trained models with your data. So that's where it comes in handy for most of the enterprise customers, meaning their enterprise data is not changed. Right. So this is a small demo, which I'll play it. This is a glimpse of the generative AI toolkit, what we developed. As you can see here, on a click of a drop down, you can select the volumes. So the volumes, I'm not sure if it's not big. I'm not sure. Yeah. So when you mount an NFS volume into Linux, and you can easily run this application, and then you can see here the NFS volume is mounted, and you can select the volume which you want to work with, and as a drop down you can see all the subfolders in that particular volume. So what happens when I actually click on that particular folder is, let me click on the particular folder. You go back. So this is a video demo. Yeah. So when I click on a particular folder, it goes and actually takes all the files. Takes on all the files and infers from the files. For example, it says this is a specific file here, and this is the key insights of the file. So based on the selection of the folder, it actually reads all the files inside the folder, and it lets you know what is inferred from that file, which is pretty awesome, because most of the cases what I see is like you don't have an option to set. You can actually ask a question without actually knowing like what folder you're working with, what is the data set you're going to work with. So in this case, we can segregate the data set based on the volume level, and you can work on the specific volume and ask questions on the specific volume, which will have a specific set of files. And also, not only that, so you can actually, we are giving an option here, like what do you want to know? Basically, you can type your question here, and it will be able to generate the answer based on the data sitting on that particular file selected on the top here. So in this case, we are actually, as a demo, I'm just clicking on like tell me more about Google Cloud NetApp volumes. It actually generates a synthetic data there, and based on the files located in this particular folder. And here you can see it provides you all the details on the top. So in this case, we use the when we started, we used the ranking based on the cosine similarity, but we are optimizing that to get a better output. And then on the top, you can see here this is basically the citations. So it doesn't actually get the data generated from a single document. It actually takes all these different documents and generates the data out of all this document. And then on the side, you can see the basically you can add your prompt. So we are adding a prompt. So it's all predefined prompt. So basically summary, people and their roles, results, document length. So what does it do? You add, it keeps on adding a column where it does say like, what are the people mentioned, what is the summary and everything. And you also have an option to choose your own prompt, which will add as another column here. Right, and then let me do this. So here we have an option like chat with your data. So what does it mean? Is what does it mean? Like you want to chat with the data, which is on that specific folder. Here you can see in this folder there are 6 different files, and you can chat with that file. So meaning like you can ask question about it, and then it will actually let you know. So in this case, we are using the suggestion questions. So and click on it. So it will actually go take those suggestions and get it and gets you an answer. So on the background, I just want to explain a simple workflow. So on the background, what we do is we take all these documents. We use the embedding model provided by Google Vertex AI platform and create the index on the vector DB. And then when we give the prompt, it takes the vector, it takes the chat history if it is there, and it also takes the metadata based on the embedding, and then it clubs everything together and sends it across to the Vertex AI platform, which results in the response of the synthetic data generated based on all these 4 parameters and gives it back. So this is all happening on the fly, and everything is developed by us on the backend. Right. So here it generated like give me 2 summary lines. It generated an output on that, and what are the key features? It provides you with an answer of the key features, and then what are the benefits? It provides you with the answer with the benefits. We also included a feature of actions here. I will show that. So these are the I would say the customer convenience features. So in this case, as you can see here, we had an option of chat and code chat and image gen. So the chat is basically we use the Bison model. This was like 3-4 months back. But right now, we are actually integrated with Gemini, which is the latest model, which is a multi-model, which has all these particular features as part of one model. But in this case, when we developed it, it was like text Bison, chat Bison, and image gen. So chat meaning it's basically for natural language processing, and the code chat is basically for generating the code. Right. So here, let me run a little bit. So what I'm saying is like, can you create an HTML product page from your responses? Yeah, so it takes all these responses from the top and it creates a HTML product page. And then what we are going to do is like we want to create a image by saying futuristic cloud. It uses the image gen model and creates this particular image. So this is part of the Vertex AI platform. And then what we are doing is like we are trying to add this generated image below the headline of the HTML page, so that when we actually see the page, the image is also embedded to the page. As you can see here, that is added as part of the headline here, and then as part of action, we are saving it to a file, and then when we click on a file, it comes up with the product page, which has all the key benefits. So this is a fantastic use case for the product marketing. If they want to create a product page, which actually want to create they don't want to go to any of the outsourcing companies to create it for them. They can use the AI. They just want to know what exactly they want and what kind of image they want, and they're good to go. So this is one of the example where we actually showcase that a use case for the product marketing. Yeah. So that's about the demo. So right now we are integrating with Gemini and also with the open source models like Claude. So what happens in this particular GenAI toolkit is like once you log into the GenAI toolkit, you choose your volume. You want to choose like you want to use Google or Azure. So if you choose Google, it provides a Gemini model on the OpenAI models, on the Cloud AI models. Based on your configuration, based on environment variables, you can configure that, and you can actually start working on it. So this is what when we actually showcased this as part of last year NetApp Insights, the yearly event. So many of the customers of NetApp are asking, like, how do we use it, right? So they want some tool like this to talk to their enterprise private data, which makes it easy for them and which is much more secure. This application is running within the VPC where they don't want to let it outside. And there are some use cases, where they want to showcase it to they want to actually let the internal customers use it for their own documents, where they can talk to their documents. Yeah. So that's about this demo. Yeah, and I want to finish off this with thought. Like, if you have any questions on NVIDIA or GCNV, or if you have any recommendations, feedback, I'm here. Please talk to me and let me know your feedback. The feedback will help. Yeah, thank you for the opportunity.
Thank you so much, Prabu. Any questions for Prabu?
Do customers know how much resources they need to serve their model? Like, do they know what the traffic might be? Is it like, does your Kubernetes cluster scale up and down depending on the load?
Oh yeah. So right now, NVIDIA. So two different examples. NVIDIA example is like where you want to have a high-end, highly scalable Kubernetes cluster. For the private, for the GenAI toolkit, it's an application. You don't need a highly scalable. But yes, for the NVIDIA, it needs a highly scalable, and we need to actually closely monitor and make sure it's running fine. Yeah. So in this case, we use the DGX cloud on on-premises, DGX on the on-premises, and on Google Cloud NetApp Volumes, we use the GPU instances provided by Google. So we started with the 2 worker nodes, 4 worker nodes, based on the model. So it also depends on what model you use. So if you are using large scale model, based on the model size and the parameters, the GPU instances, worker nodes will differ. Yeah.
Great presentation, by the way.
Thank you.
And my question is towards the NVIDIA example that you gave. So the tagline was how to securely communicate with your own data. Now, I got the explanation, but like, what was the secure aspect of it? Like, how was data anonymization being a part of it? Like the sensitive nature of data, which probably I would not want in the form of responses, or would I want that? Like, how was that, the secure part dealt in that?
Okay, so in this case, most of the customers, it's for their internal use cases where they can develop their web applications, Copilot or chat, and they can provide it as a part of a secure environment to their internal customers, right? So in this case, you can take an example of NetApp. So NetApp Chat GPT, it's basically a private instance for NetApp, and it's more secured. And also you cannot actually use NetApp Chat GPT outside of your VPN. So it's more secure in that way. So in this example, they can have their customers within their VPN or without their VPN, but it's all part of their network. It's all not going out of the network for the internal customers. For the external customers, it might be different. So external customers will be using their Nemo retriever, which is in the cloud, which is actually deployable as part of their network. Yeah, it's more NVIDIA is more like on-premises right now. And if it is on the cloud, then you will be installing the Nemo microservices in your network, so you can actually have a full privilege of managing how you want to structure your network and doesn't actually go out.
Thanks for the response.
Any other questions? Thanks, Prabu. Our next speaker is Selvi.
Thank you.
Can you all hear me through the mic? Okay, great. Okay, good evening, everyone. Thank you so much for coming by. I know this is all personal gym time, homemade cook time. Thank you for allocating this time to hear us. I am Selvi Kadirvel. I'm from a seed-stage startup called Elotl. We are headquartered in San Francisco. We build 2 products. I'll be talking about Nova, which is our Kubernetes fleet manager. We have another product called Luna, which is an intelligent cluster autoscaler also for Kubernetes. A little bit about my technical background. Before Elotl, I've been about 8 years in the container management and Kubernetes management space at Cisco and ContainerX before this. And prior to that, I was in the field of AI ops, which is using AI for improving infrastructure management. Coincidentally, and before that, I did my PhD also in the field of AI ops at the University of Florida. Coincidentally, someone from every one of these companies and my colleagues happen to be here in the audience today. So yeah, thank you so much. It was great catching up with every one of you. So this will be the outline of our talk today. We'll start with talking about what exactly is a fleet manager, what are its day 0 and day 2 capabilities, and a core component in a fleet manager, which is a schedule policy, which is what maps your workloads, GenAI in this case, and the focus of this talk, across an infrastructure that could be on-prem or cloud clusters. We then talk about the needs of healthcare GenAI apps and how a fleet manager can help satisfy these various infra and data needs. Finally, we'll end with a demo of a drug research Q&A app that we built in collaboration with Red Hat. Okay, so what is a Kubernetes fleet manager? It helps orchestrate your Kubernetes workloads across a multi-cluster, multi-cloud environment. How does it work? It works by providing a single Kubernetes endpoint to your workloads and abstracts away a bunch of workload clusters. And what it accepts as input is your typical Kubernetes workloads, unchanged, no modifications needed by your app developers. In addition, what it requires is a schedule policy. This is a Kubernetes native way of specifying the mapping, and I'll get into detail of what types of policies are possible through Nova. A simple mental model to think of a fleet manager is to think of what Kubernetes does for nodes in your data center. Your Kubernetes pod, you don't need to know how many nodes you have available in your cluster. What is its capacity? What resources are available now? Did a node fail? Did my pod have to be rescheduled? None of these things are things you need to know as a Kubernetes user. This is exactly what we want to do at the multi-cluster level. So your workload need not know which cluster is the best suitable at this point. If a cluster goes down, Nova is capable of rescheduling your workloads, migrating it for performance reasons or failure resilience reasons. So many of you are already using some sort of a console or user interface where you are able to view your clusters. So that does look like a multi-cluster manager. So how is that different from a fleet manager? The key difference is that in a typical multi-cluster manager or console, your cluster is the first-class entity. So you care about cluster lifecycle management, how that was created, when that's going to be upgraded, is that satisfying your needs. Whereas in a fleet manager, your workload becomes the first-class entity that you care about. In the last couple of years, we've seen an increasing resurgence of the importance of fleet managers. This has been because of the wide adoption of Kubernetes clusters and the operational complexity that comes along with this. So currently, you do have cloud providers providing their own fleet managers. So if you were to create a GKE or AKS cluster, you'd be asked in the 3rd or 4th step, hey, do you want to connect it to your fleet? Nova is different in that it is very similar in its functionality, but it is cloud agnostic, which is what makes you be able to manage your on-prem and cloud clusters through the same control plane. We've also talked with a number of our partners who also build custom fleet managers where they do not want all the generic capabilities that we'll be talking about today. They have very specific needs and they build their own fleet managers. So now that we have a high-level overview of what a fleet manager is, we'll look into day 0 and day 2 capabilities. The first one is the ability to capture a static placement policy. So this would mean your production customer-facing app A needs to be on cluster B on region C. This schedule policy can capture it through Kubernetes manifest. This is fine. This is essential. You need that level of abstraction because you don't want to hard code your cluster names within your CI/CD pipelines. But the more interesting one comes in during the dynamic placement of your workloads. Here, for example, if you were a machine learning researcher, all you wanted to do is place your workload in any one of your cluster, 3 dev clusters in your team. You don't want to know, hey, dev 1 is in maintenance mode, go place it on dev 2. You want to be able to specify that. And especially as an app developer, you don't want to even know that. You want your platform team to be able to define that policy. So that's what Nova helps you with. The third use case is the standardization of workload clusters. So you'd have a bunch of clusters which need similar, say, your logging, monitoring, and analytics stack. This is something that's defined by your ops team, and they'll be able to set up all of these on all of your clusters through the fleet manager. We use something called the spread policy, which can duplicate resources such as secrets or larger stacks onto all of your clusters. Okay, so before we go into day 2 capabilities, let's look at what does a schedule policy look like. It captures 2 main questions, whereas which of your subset of resources are governed by a specific policy, and also which of your subset of clusters will be targeted for that workload. So in the case of resources, you can use labels, you can use namespaces to define them. In the case of target clusters, we provide a wide variety of labels and expressions through which you can specify policy. On the right is a very simplified YAML file. We'll look at a couple of examples that are easier to follow through. So policy 1 here says that for all apps with label app data ingestion v2, choose any one of my dev clusters. So this was the first example that we talked about. On the right is a second policy where we say another app, say model v1, you want it to be in, say, your East 1 and East 2 clusters, but you're not yet ready to deploy it on your West 1 clusters for, say, some user load regions. So you have include and exclusion policies. What we're not showing are the more advanced policies. We have something called a spread policy, in which, for example, if you were to deploy Istio on a bunch of your dev clusters, and you want certain parts of your manifest to be overridden, the schedule policy can capture that. So, yeah. Okay. Fleet Manager's day 2 capabilities. So I won't go into the depths of this, but I'll give you an idea of what this is. For example, workload rescheduling. A number of factors in this environment can change. For example, an ops engineer decides to actually edit the schedule policy and change a placement, which is the most straightforward way in which you would cause trigger a migration. A second use case would be, say, a particular deployment is being changed from, say, 10 replicas to 100 replicas because your user load spiked or your data sources changed. In which case, Nova is continually reconciling the status of the infrastructure and the resource needs and matching or moving your workloads to the right cluster. Another feature that we have, which is not available in other fleet managers, is called just-in-time compute or on-demand clusters. So if you have a particular cloud cluster that has very low utilization, Nova can bring down all its worker nodes and keep only the control plane up, or it can delete the entire cluster. And vice versa. If you have a workload coming in that can't be satisfied with your current set of clusters, it can bring up a cluster using an existing one as a template or a golden image. So very similar to what a node autoscaler does is what Nova does for cluster level. Okay, so let's talk about the particular GenAI application that we worked on. This was done in collaboration with Red Hat, as I mentioned earlier. So a typical pipeline could consist of everything from data pre-processing, model training, fine-tuning, embedding, all the way to inference and evaluation of your models. In this particular case, there were certain components that made sense, and which is what we'll be showing. We specifically built out a drug research Q&A app. We used a very small Mosaic ML 7 billion model, as our previous speaker said, open source model from Hugging Face. Our choice was based on cost effectiveness and also ability to run large experiments using this model. Our input data was drug research journal paper abstract that was available in the open source. At the bottom bullet point is the set of components in our pipeline. The first one is an event trigger for data availability. So in this particular use case, customers wanted to be able to have new data sources coming in at different time intervals, and the entire pipeline needed to be triggered by this availability. The second step is the conversion of these text data into an embedding, which is then stored in a vector database. We experimented with VV8 Vector DB as well as the vector library from Facebook FAIRS. Then we used self-hosted LLM models to truly experiment with the scheduling decisions. And finally, we wanted to use RAG because a lot of proprietary data had to be augmented to the base models to make this pipeline work. Okay. So this is a graphical representation of the pipeline that I just described. We'll kind of walk through it through the blue numbered circles. So right in the center is the data team, number 1, which is producing the document data source. Number 2, we used AWS's message queue, the SQS service. This would be the trigger for our AI pipeline. As soon as data comes in, we have a job come up. We use KEDA, which is Kubernetes event-driven autoscaler. This is simply an operator that's running on your clusters that says, hey, new data source came in, I'm going to start up a job. This job will read the input text data and convert it into embeddings and store it in our vector DB. That's shown by number 4. The data embedding, we used LangChain packages to be able to do that. Number 5 shows the vector DB, which consists of, within each yellow box is the green boxes, which corresponds to the Kubernetes workloads. So vector DB database was a service and a deployment. At the bottom is the drug researcher who's interested in this Q&A app. Number 6 represents a query that's being sent to our RAG service endpoint, which then talks to both the vector database and as well as the LLM model and produces a result, which is number 9. So let's go on to talk about how the specific infra and data needs of this pipeline was able to be fulfilled by a fleet manager. First is the infra needs. The customers typically wanted an on-prem and cloud approach or a multi-cloud approach. The reason was that CPU and GPU availability. A lot of companies had GPUs already invested in local GPU clusters, and they only wanted to use CPU clusters for on the GPU clusters in the cloud if all of the on-prem resources were fully utilized. Then within the data pipeline itself, different components had different needs. For example, the LLM and data embedding jobs needed GPU clusters, whereas the vector DBs depended on the similarity search algorithm. Some of them could do with CPU, some of them could do with GPUs. So the multi-cloud scope of the fleet manager, as well as the scheduling policy flexibilities, allowed us to capture this. Then we go on to data needs. Data gravity was a key concern. Some of this proprietary data has PII or personally identifiable information. In this case, the data ingestion job had to be run on-prem and could not be scheduled on the cloud. Also, non-PII data was available in different clusters at different points in time, which meant that the actual Kubernetes workload needed to be migrated from one cluster to another cluster. And our scheduler allowed that to be easy to run. Finally, operational complexity. We didn't want the app developer to have to run anything or add anything new to their manifests. If you can run Kubernetes on single cluster, you would be able to use our fleet manager and be able to spread your workloads across clusters. That was our goal. Finally, we also provided a separation of concern, which means that the schedule policy is something that the app developer does not define. It's the platform team that defines that, and it doesn't become a burden on the app developer. Okay, so let's look at this in action. I show you the demo of the app. But before we start looking at a number of terminal screens, a quick overview of the clusters you'll see, the jobs you'll see. On top is the document data store as well as the message queue, which is a part of the event trigger. We use AWS cloud services for it. These were not on our clusters. Everything else below the top 2 boxes are on Kubernetes clusters. On the right, on the green boxes, we have clusters on one cloud, EKS. This held the CADA operator, the CADA scaler, these CADA scaled jobs, the LLM model, self-hosted, and a service endpoint for it, as well as the RAG generation query service. On the right, on the red boxes, is the second cloud. After day 0, we'll show what needed to be done to migrate some components of the pipeline into the second cloud provider. At the bottom is the end user who is interested in this Q&A app. Okay. So at first, I'm sorry, I'm going to read that out to you. It doesn't look too big. So we're talking to the Nova control plane. We're saying, is that really loud? Okay. Hopefully some of the screens closer to you might be a little better. Let me see, I can zoom in. Because it's full screen, I don't think it's letting me zoom in. Yeah. Okay, most of it will be highlighted with text describing what we're showing, so I'm also going to talk through it. So here we show a kubectl command that simply talks to the Nova control plane and says get clusters. Typically, cluster is not an object that your Kubernetes cluster would know of. The Nova control plane has a custom resource called cluster. Here, we are managing 10 clusters across 2 cloud providers, GKE and EKS here. They are spread across different regions. We then describe the custom resource cluster to see what that contains. What we just highlighted was It knows about the CPU, memory, as well as the number of GPUs available in each cluster. This is what allows us to define the schedule policies to deploy your components onto your fleet. Okay, Nova also adds some specific custom labels to each managed cluster. This includes the region it's present on, the zone it's present on, the Kubernetes versions, as well as the providers. Okay, the second step is the workloads deployed on the fleet manager. So here's an example of a manifest. It's the CADA scaled job, which is basically a wrapper around a typical Kubernetes job. We connect it to a trigger, which is the AWS SQS queuing system. All that needs is an SQS URL and a secret that can determine whether or not your document store received a new data set. This is what is going to determine when our AI pipeline begins. Here we use load data from a document data store and move it into a VV8 vector DB. We then look at another, the self-hosted LLM model, which is Mosaic ML 7 billion model. We show that it requires 1 GPU. This is able to run on a G5 X large, so it was pretty small. We then show an example of a schedule policy. This is a standardization of the workload cluster policy, which means take a secret and make sure it's available on every one of your workload clusters, because both of them are going to serve as source and destinations of your workloads. We have similar policies for the namespace, which we also expect to be standard on all clusters. Then we deployed the RAG and LLM components. We see that because of the policies we defined, the LLM model got deployed on cluster on-prem 1. The RAG service got deployed on another cluster on-prem 2. They were both defined by different policies. And then we then talk to the Nova control plane and say, hey, you got your deployments up. Tell me what my services are. Tell me what their public endpoint APIs are. And I'll be able to access the Q&A service after that. So here we see that this is the IP address of the RAG service. So we just use a Postman API. We talk to it. We ask a question about a summary of a particular study. We get a reasonably brief answer. And so this is day 0, what we saw. We had a bunch of workloads, about a couple of dozen workloads. We had about 10 clusters. The components were placed in the right clusters that we expected, and we were able to access the Q&A service. Say a few weeks down the line, we have a new data set that's coming up in a new cloud. We look at how we can migrate this data pipeline into the new cluster. So we look at what the policy defined for the particular RAG service. We won't move all the components. As a sample, we'll just move one component. We see that it requires a cluster with a particular label. So we go ahead and edit our custom resource, which is our cluster, and add this label to change the target cluster. And we apply these policies, and we wait for the deployment to become available. Once it does, we see that the target cluster has changed from on-prem 2 to Cloud C, and the name of the policy comes up. Okay, we note the new IP address at which it is available. We go make another query. We see that the same Q&A service continues to remain available. So what we just saw was day 0 scheduling of workloads, and then day 2 application mobility across clusters. Okay, so in summary, what we showed is that fleet managers can be a critical component and helpful component in your AI infrastructure. We see that both for, like as we showed, initial placement, mobility, cost-effective resource usage is what its initial goals are. Currently, we are working on a number of extensions. We've heard from partners that they'd like priority-based scheduling. So you want to be able to say, hey, prioritize cluster 1 and 2. If that's not available, then go to cluster 2, rather than providing subsets and inclusion and exclusion rates. So that's what we're working on. We're also working on deploying frameworks. Say, Ray is a distributed AI/ML framework across multiple clusters. And we're also working on cost-based placement policies, so that in addition to just resource availability, price performance values can be taken into account to make these placement decisions. In today's talk, we looked at Nova as a fleet manager for specifically AI workloads. But because a fleet manager is in the path of your workload, as well as has visibility and control to your workloads, it can be used for a number of application orchestration aspects. namely disaster recovery and high availability. So we have a lot of other use cases too that you can take a look at our website. Nova is free for managed clusters up to 6. So please give it a run and let us know what you think. Happy to take any questions.
What's a typical latency you're seeing if you migrate an application, let's say, from one cluster to another, especially if you go from on-prem to cloud, right? Will there be any interruption or some sort of delay that user will see?
There will be some interruption, but it depends on the particular. In this case, it was just about I think it was about a dozen workload items. So it was a few deployments with services. So it was less than a minute. Yeah.
Any other questions for Selvi? Thank you so much, Selvi.
Okay. Thank you.
Our next speaker is Noah from Predibase. And while we are waiting for Noah to set up, there's some T-shirts. The restrooms are there. I think the pizza is gone. Sorry.
Alrighty, cool. Hello, everyone. My name is Noah Yoshida. I am from Predibase, and today I will be talking about kind of how we've used a multi-cluster Kubernetes kind of architecture to build our platform at Predibase. Cool. So a little bit about me. I'm a staff software engineer at Predibase on the serving team. So my team handles all of the infra, all of the serving for the LLMs that our customers train on us. A little bit of background about Predibase. We're a company about, I think, like 25 people right now. We've been around for about 3 years. We recently-ish pivoted to LLMs. We were doing deep learning and kind of like AutoML type stuff the first 2 years. And then with ChatGPT, LLMs took over. So we kind of leveraged our expertise in deep learning to focus more on that. So yeah, at Predibase, it's pretty much, we're all about LLMs. So fine-tuning them, deploying them, and then prompting them. So kind of like the whole life cycle. Specifically at Predibase, we are interested in efficiently fine-tuning and serving these LLMs. So we only do adapter-based fine-tuning right now. If you're not familiar with what that is, essentially, instead of doing like a really, really big fine-tuning job that takes a lot of data and might take several days to weeks to accomplish, instead you can train an adapter in like a matter of minutes with the right GPUs and configurations, and then immediately start seeing results on your base model. So yeah, that's a little bit about Predibase. I won't go in too much about that. It's more Kubernetes focused for now. But if you're interested to hear more, definitely talk to me after. Yeah, so working at Predibase, one of the things that we've discovered recently with LLMs is that it's kind of tough to get it right. There's a lot of different challenges in the world of building an LLM serving platform. One of them is GPU scarcity. So if anyone knows where to find A100s that you can auto-scale off and on in a Kubernetes cluster, please let me know. I'm on the lookout. I don't think there's anything that exists right now that lets you do that. CoreWeave is out of capacity. Google, you have to wait like 2 hours to auto-scale. So if that exists, please let me know. But currently, we're working with like a pretty scarce budget of compute. Additionally, I think, like the first talk said, data privacy is a very big deal. People don't want their data leaving their environment, and that, compounded with the GPU problem, creates a whole mess. Finally, working with LLMs can be a bit tricky because LLMs themselves can be large, large language model. There are a lot of weights. The container images to run them can be quite large as well. They're machine learning, container images, so they have CUDA and whatnot. So all of these, points are kind of tough to overcome. But thankfully, we have Kubernetes and we have, a multi-cluster architecture that'll try to get around all of this. So in particular, for the GPU scarcity, one of the things that we've done is leverage multiple Kubernetes clusters to find compute. So if we're running in AWS and it has, AWS has certain NVIDIA GPUs that are readily available and others that are not, we can actually have clusters in different clouds, maybe some more niche kind of GPU clouds that actually have those available for us. Additionally, if customers are worried about data leaving their environment, we can have kind of workload clusters running in their VPC. So all the training and all the inference happens there. Data never leaves, customers happy. Finally, there's some more like interesting things you can do with using Kubernetes clusters as kind of, I don't know, like resources. I'll get into that at the end, but yeah. So just a brief overview of the Predibase architecture, particularly as it pertains to serving. We use multiple clusters. Normally, we have one control plane and many data planes. Here, it's just one and one. So each of these lives in its own cluster. They're connected via Istio, which is a service mesh provider. For those who don't know, essentially, it just lets us communicate between the clusters as if the services in them were all in the same cluster. In the control plane, we have our gateway, which receives requests, and a workflow orchestrator, which kind of organizes like which cluster will do what type of work. And then in each cluster, we have agents running that actually configure the LLMs once they're deployed. So yeah, the normal provisioning workflow just looks like the request comes in through the gateway, goes to the orchestrator. All of the agents are pulling work from the orchestrator, and then they will go and start the LLM. And side note here, we'll get into this later. Starting the LLM can be a bit tricky. You have to like download the model weights if they're not already on the node. So that happens kind of at the data plane level as well. And then finally, for inference, so once the LLM's up, the current architecture is that all of our requests go through our centralized control plane because we have to do authentication, make sure the user is allowed to talk to that LLM. If it's one of our serverless LLMs that are kind of shared by everyone, we have to rate limit people so they don't bring the LLM down for other customers. And then finally, we need to route the request to the correct pods, and that's all done with the Istio virtual service. So once all that happens, it goes to the data plane, the request comes back, customer's happy. Kind of like I mentioned earlier, the kind of overall Predibase architecture is that there's one centralized control plane with many data planes. There's two ways that customers really run, compute on Predibase. One of them is the VPC mode, where we install a data plane in a customer's VPC. It could be AWS, Azure, Google. That's all kind of automated on our end, but the end result is there's a Kubernetes cluster running that's part of the service mesh, and we're able to talk to it. The second, and kind of my more preferred way of people running stuff on Predibase is through our managed AI cloud. So what that is the customers essentially running all their compute on our GPU cloud that we're running in the back end. As I mentioned earlier, we've had to do some stuff where we route workloads to different clusters based on the type of GPU that we need. I'll show that a bit later. But yeah, so broadly, there's these two kinds of modes to deploy Predibase. So taking a little bit deeper dive into the AI cloud and kind of how multi-cluster Kubernetes is helping us there. So as mentioned, every cloud seems to have different GPUs available. So AWS, for example, has a lot of A10Gs, which are fine. They don't have a lot of GPU memory, though. So if you want to run really large models, You can't really use A10Gs. On the flip side, we have an on-prem data center where we actually bought A100s and L40s. Like I said earlier, though, there's like no way that we could auto-scale these off and on. They're kind of, you turn them on and they sit there. So as you can see, they're kind of different, let's say, like attributes to these clusters, right? So on one end, I'll just skip ahead. One end, we have the AWS cluster, which can actually auto-scale these A10Gs off and on. Unfortunately, because LLMs are large, containers are large, it actually takes like 10 to 15 minutes sometimes to acquire a new node, download the AMI, start it up. But the nice thing is it's AWS, there's pseudo unlimited capacity. So if we really need to, we can scale into the A10G AWS data plane and go from there. But if we have room, it would be better if we actually go into the on-prem data plane. And this all happens kind of at the application level for Predibase. So when you submit a request to start an LLM, we kind of route the request and start the LLM in a different data center based on the accelerator type you defined. So for A100s and L40s, while there is no additional nodes coming into the cluster, we do have a pretty good number of them. So if there's availability, the pod starts in like under a minute because everything's pre-cached on the nodes. And in general, these nodes are way faster, so you'll get better performance. And I was kind of mentioning this earlier. One of the tricky things about multi-cloud is how do you manage like artifacts that need to go to all these different workload clusters. So for one of the examples that we've run into a lot and had to overcome was the model weights and container image being really large and taking forever to download. So the solution for the on-prem cluster was very obvious. You just pre-cache everything there. Obviously can't do that, though, with AWS because these nodes are coming up and down very frequently. So we've done a lot of optimizations around that to try to like compress the images, compress the weights, store them in different formats, change the way we're downloading them. But that's just kind of an aside there that things that work really well for one type of Kubernetes cluster, like one on-prem, for example, can pose a challenge in an auto-scaling situation. So anyway, yeah. So that kind of has solved our GPU scarcity problem. So what about security? Well, the cool thing about Istio is that it does a lot of like network configuration for you, or you can configure a lot of network stuff with it. So one of the things we've been able to do is create these authorization policies. So all of the different clusters, while our control plane is allowed to talk to all of them, they are not allowed to talk to each other. So every single data plane, so including the Predibase managed one, and then obviously every customer's private data plane, they're all kind of siloed. So they're only allowed to talk to the control plane and not each other. And then in terms of data privacy, taking a bit of a deep dive into the customer's data plane. So what it looks like is there's just a Kubernetes cluster with auto-scaling GPU nodes like normal. But this is all within a private VPC in their cloud. So within that private VPC, normally we see stuff like the customer's data source. If they're like fine-tuning an LLM, they'll store all the kind of training data there. And then there is a bucket where we put all the model artifacts. So during fine-tuning, all of the data is ingested through that, in that private VPC from the data source. Normally that's not even publicly accessible. And then all the model artifacts are written back to the bucket, which is, again, normally like tightly controlled by the customer so that no one can just like go and download their weights. And then finally, when we do start an LLM, it's running in that VPC, and since it's there, it can read the S3 bucket or just any bucket and download the weights from there. So that way, as you can see, none of the data has actually ever left the customer's environment. And this is really nice because we didn't have to deploy an entire control plane in the customer environment. We only needed to deploy the data plane, which is pretty minimal. So currently, for inference, as mentioned earlier, there's like an authentication service that happens, and all the inference goes through the Predibase central control plane. In practice, what this means is that there are prompts and like prompt results flowing through the control plane, and we found, for obvious reasons, some customers aren't really happy with this. So something that's coming in like the next few weeks for us is direct ingress, which will be just kind of opening up a load balancer in the private VPC and having it only accessible within that VPC, so then customers can directly talk to the LLMs through there. So, in about a month, I'd say we'll have a completely private VPC story where customers' data for fine-tuning, their model weights, and finally the prompts are all self-contained in the customer's VPC. So that was really nice. What else can we do with multiple clusters? So one of the things that happened about 2 months ago is it was the weekend. I open up Slack on Monday, and I see that one of the test data planes that we had in one of our kind of smaller GPU clouds had just gone down. It was completely gone. None of the prompts were working. And that was really bad. So this prompted some investigation into how we could do failover with multiple clusters. So like I said, if the entire cluster is down, that's really bad. We don't want that to happen. And if it does happen, it should recover in some way. So what we actually found is that through Istio, you can configure a thing called a destination rule. And what this does is it lets you route traffic based on the health of the kind of downstream applications. So for example, if the first cluster is, if all the requests going to it are returning like 500s, for example, you can configure it to actually route traffic to a different cluster. So we ended up doing that. It routes traffic to a second cluster where normally the LLMs are all scaled down to 0 so that we can use it for other stuff. But in the event of a disaster, it'll go there. And we actually use the Kita autoscaler as well. So Kita is kind of sitting in front of that, holds onto the request, scales up the LLM, and then the prompt goes through. So with all the kind of auto-scaling optimizations we've done for our on-prem clusters, we've gotten that down to be about like 30 seconds. So 30 seconds isn't great for a prompt, but it's better than it never going through. And yeah, this was just a little detail about how that auto-scaling is actually working. It just comes in through a gateway. We're using the Kita proxy instead of just vanilla Kita. So what that does is it just holds onto the request, and it talks to Kita to say, hey, this request is going to a certain deployment. Is the deployment running? Like, are there any pods running for that deployment? If not, it will trigger the deployment to auto scale and then route the request through the normal kind of service, Kubernetes service once the pods are up. So this was a really fun. So finally, this was the thing I was alluding to earlier. You can do very interesting things when you have a bunch of Kubernetes clusters and you're messing around with Istio. So one of them is an investigation we're doing into federated ingress. So what I mean by that is one of our customers came to us and they said, hey, Predibase, you guys are cool, but it is taking a really, really long time to get a first token response back. And so for those maybe new to LLMs, time to first token is one of the kind of key metrics that people judge your platform on. So normally it's throughput, time to first token. What time to first token normally is when you start typing like, hello, write me a poem, how long it takes to return that first character, and then kind of start streaming the response is what we're referring to here. And in general, you want about 150 milliseconds or less to make it feel like a real-time kind of chat with a person or with a cool LLM. Anything above that and it feels a little disjointed where you'll type it in, you'll hit enter, you'll wait a little bit and the response comes. So customer, it's like, hey, you guys are cool, but it's taking like 400 milliseconds. That's not really acceptable. So what we realized is that because our control plane does all of the ingress, we were going from the customer's location in New York all the way across the country to our control plane in Oregon, all the way down to Texas, which is where our data plane was running, and back. So obviously going around the United States, even at the speed of light, can be a little bit slow. So how do we fix this? So one of the ways we could fix it would be with that direct ingress for VPCs. But one of the kind of trade-offs we made there is that the VPC direct ingress won't really have any auth in front of it. It's a private endpoint in the VPC, so at least for the initial design. We're trusting the customer doesn't let anyone use that endpoint that's not allowed to. But that doesn't really help us with our kind of managed data plane. So how do we fix that? Well, one of the kind of weird ideas that we had, which ended up working very well, is we create a bunch of Kubernetes clusters all around the country, all running a very minimal deployment of Predibase, which just contains the rate limit service, the auth service, and yeah, that's it. And then what happens is there's a thing called AWS Global Accelerator. So whenever the customer goes and types in serving.predibase.com, it actually finds the closest AWS data center, routes the request in there, and as a side effect of that, it'll try to route it to the closest kind of load balancer that we have. And if the load balancer is running in a Kubernetes cluster that's close to the customer, then it'll immediately kind of enter our United States spanning service mesh there. And then from there, it can go directly to our data plane. So normally, this kind of, you could achieve this kind of network routing at a bunch of different layers. If you're really good with load balancers, AWS, you could do it that way. We're a little bit better at Kubernetes, less so at that. So this was the approach that took about half a data prototype, ended up working. And we're a small startup, and iteration time really matters. So this is what we stuck with. So with some testing, we found that the time to first token went down from 300 to 450 milliseconds for people on the East Coast, all the way down to less than 200, which is about where we want to be. So obviously, it would be much better if the data planes themselves were closer to the customers. If anyone has a lot of money and wants to help us buy more GPUs, please let me know. But until then, this is what we're working with. So yeah, pretty happy with this result. And I think it kind of speaks to the power of using Kubernetes as a very generalized platform for doing compute. Yeah, so this is essentially what it looks like now, all the way back from this. So as you can see, the lines are a bit more direct, so that's a win. Finally, I think I'd be a little remiss if I didn't mention about this. So there's a lot of open source kind of LLM serving platforms. How is Predibase different? One of the things I mentioned earlier is that we focus mostly on adapter-based fine-tuning, but we do have an adapter-based serving solution called Lorax. That it's fully open source if you want to look it up. It originated as a fork of Hugging Face's text generation inference server when they changed the license on that. That was the whole thing. But it's diverged quite a bit from there. We've put a lot of optimizations in where you can actually run a single base model and have multiple adapters, so essentially fine-tuned models running on top of it. So for one GPU, you can kind of extract the value of many different ones. And the way we do that is we dynamically load the adapter weights, which are essentially like a patch on the LLM, so to speak, to make it behave a bit differently. So you can dynamically load those at query time instead of when the server starts up, it's like as the prompt comes in. Since adapters are really small, you can do this very quickly, so loading and unloading these from the GPU. As well as there's a lot of optimizations around queuing, so like while one request is going, we can load the adapter for another one and so forth. So yeah, that's just a little spiel about some things we do at Predibase to make serving a bit faster, a bit more efficient, and there's a lot more that we're doing literally every single week, stuff like Medusa decoding, other speculative decoding, algorithms. So if you're interested in that, definitely let me know, and we can chat after. But yeah, thank you so much. Again, here's a QR code for a free trial. If you're interested, you get some free credits when you sign up, so definitely, if you're at all interested in LLMs, give us a try. And yeah, I would love to connect on LinkedIn afterwards. And yeah, if you're interested in anything else about Predibase or just want to talk about Kubernetes, feel free to connect. I think my coworkers are tired of me yapping about Kubernetes at work. So yeah, thank you for listening.
Thanks so much, Noah. I have a question about the data plane. Other than HA, is there any other use case where you need more than one Kubernetes control plane for your data plane?
Yeah, so there could be a situation where we want multiple control planes. I think one of them that would make the most sense is having regional control planes to decrease latency for customers all around the world. So currently, if you're in Europe and you try to use Predibase, it's a little slow because everything has to go all the way to US West 2. Ideally, we would have control planes in many different regions, but currently it's just a single one.
Sorry, I meant the data plane.
Oh.
For the data plane, do you see any need for multiple Kubernetes control planes?
Oh, I see.
You see a need for multiple clusters other than the HA use case you spoke about?
Yeah, yeah. So the high availability is good. I'd say just being able to run a bunch of different clusters on different GPU cloud providers to maximize the number of GPUs that we can use would be very important. So.
Cool. Yeah. So one Kubernetes cluster per GPU provider. You don't envision the need for multiple Kubernetes clusters inside a single GPU cloud provider for a single customer.
Yeah, I guess that would be interesting to do if we had multiple. One of the things that would be interesting actually is these private VPC customers. Everyone has different security requirements and tolerations for risk. So some of them I think would be okay with having their own kind of dedicated cluster, even if it was outside of their VPC, as long as they have a guarantee that only your workloads run here, only your LLMs will be running this, and then they could set up some link, private link to their data. So yeah, I could see that being useful.
Cool, thanks. Any other questions? Thank you, Noah.
Cool.
Thanks to our hosts, Xiaoyun, Richard, Yuk, and Pradeep, and NetApp for hosting us. And our speakers, Selvi, Noah, and Prabu. Yes, Prabu. Thanks for the amazing content. I think all three talks really connected well, and thanks to our audience for showing up on a weeknight. Our next meetup will be at Any Scale, and it'll be Ray themed. So please do join us in July.